Yep. Our final talk for today is leveraging Easy for WRF simulations at scale on Azure HPC. To Hugo and David.
Hi, good evening, good day. This is Hugo Meijland. Together with David Evanzo, we're trying to share a little bit our experiences and learnings that we had over the last few months, where we were using Easy for trying some WRF simulations at reasonable scale on Azure HPC to learn how the Easy stack works, how to get applications added to the Easy stack, and pretty much focus on the Infiniband connectivity within Azure. So first, a little bit an explanation of who we are and what we do. David and myself are part of the customer advisory team within Azure Engineering, where we work with different high-performance compute customers, basically with two goals. The initial goal is to make sure that we help our customers move forward, but we also have a second goal, and that is actually to learn and to learn about the different workloads and how to improve Azure. And especially improve Azure to run HPC better. So with that, there's a clear difference between what we are doing and what a typical HPC admin is doing. We are very much focusing on helping set up the infrastructure, make sure we meet the performance requirements, but clearly step away, or should be able to step away at some point in time and hand over the day-to-day admin tasks to the customer themselves. That being said, when setting up clusters, when getting them ready for production, we definitely feel the same application delivery pains as most of you will do without help of EasyBuild and Easy. So that is one of the reasons why we very much like Easy, the concept, and try to see what it can do in conjunction with Azure HPC. We realized that Easy as an open source project is not only taking, we also want to give back to Easy. And with that, we're trying to do a couple of things. The main thing is what we like to take and use is make sure that Easy is actually running really well in Azure. So that means we have a quite a large fleet, which I will show later on, with Infiniband enabled HPC nodes. We want to make sure that Easy is running very well, and all the applications that Easy is delivering are running very well on those different nodes. With that, we want to contribute back to Easy different applications that we encounter that our customers are using in a more extensive way, and make sure that the Easy stack becomes more and more complete, getting closer to production, so that the Easy stack can be used by anyone in the field, but especially also by our customers. Second to that, we want to use this to verify application regression on our fleet by having the end-to-end applications in a sort of like predictable way, and hopefully in the future also including different benchmark data sets. We can use reframe testing for verification of our fleet. Also, we want to make Easy available. I was going to say to make Easy available. And with that, we are today focusing on sort of like two projects, making sure that the end-to-end on Azure is working fine. We have a project within Azure, which is called AZ Hub, which is our HPC on-demand platform, and we are already adding the Easy stack there as sort of like a pre-production preview. Also, we are working with a public project, Cluster in the Cloud, by Bristol University, and make sure that the Azure support is also being added to that project. What is a little bit different from working with Azure than with an on-premise data center is here you see a snapshot which gives you on the left side the Americas, on the right side Europe. As you can see, we have quite a few data centers. Well, not all the data centers contain high performance compute nodes. Quite a significant do, and especially our hero data centers have quite a fleet of HPC and Infiniband enabled nodes. As you can imagine, we do not have a single Infiniband network covering the whole world. That is definitely not the case. First of all, let me show you a couple of generations of nodes that are Infiniband enabled. On the top graph, you see the CPU-based nodes. Roughly, I would say 6 years ago, we started with well, actually, to be honest, before then, there was the A9 and A10 nodes, which were already with QDR enabled Infiniband. Those are end of life at this moment, so there are not too many references of that. About 6 years ago, we started out with the H16 series, Haswell series, that was already FDR enabled. A couple of years later, we added the Skylake there, and we also added the first AMD nodes to it. Today, we came in a more, I would say, predictable rhythm there. And if you followed the last supercompute sessions, the one out of 2021 and 2020, you've seen that in 2020, we announced the AMD Rome-based, and in 2021, we announced the AMD Milan-based CPU SKUs. That being said, the Milan-based are being migrated to the Milan X. So that is being done right now. We don't only have CPU-enabled SKUs with Infiniband. We have also a whole bunch of GPU-enabled SKUs, and especially the largest one are quite interesting because there's not a single NIC in there, but there are, if you look at the A100-enabled ones, those are nodes with 8 times A100 GPUs and also 8 times HDR Infiniband in there. So that's quite an interesting network. It's also NVLink, by the way, between the GPUs. I won't go deeper into that one. We're focusing on the CPU-enabled nodes first, because that is what the EasyBuild stack supports today. Hopefully, moving forward, we can also enable EasyBuild for the GPU nodes. Few remarks more on Infiniband on Azure, because it's not entirely trivial, and I wanted to use this also to do a little bit of deeper insights and explanations on how we use it. So our focus for Infiniband is purely on compute. So we use Infiniband for MPI and for nickel. We do not use it for storage. And our Infiniband connectivity is also not heterogeneous. Basically, if you look at a stamp, which is basically the analog of a cluster, that is how the IB connectivity is limited. Let me switch to another slide here to illustrate that a little bit. Here on the left and right side, you see 2 clusters. The left side is a CPU-enabled cluster with a simple 1U servers. On the right side, you see probably a GPU-enabled cluster with 4U clusters. And as you can try to count them on the left and the right side. On the front side, there are roughly 10 racks. On the back, there are 10 racks, and there's a Mellanox connectivity in the center. So here on the left side, that is one stamp. On the right side, you see a second stamp. So the connectivity here, the Infiniband connectivity, is only limited to these single stamps. That is great. but a single stamp will not give us the capacity for compute that we need in most of the regions. So that means there are most of the times there are multiple of these stamps for a single VM type in a single region. So that means that it's a little bit, you have to know what to do. If you enable 2 VMs, you will not get connectivity by default or for sure. 2 steps in between. The Infiniband is enabled, the Mellanox Infiniband is enabled using Azure IFV. In this case, I'm showing you the output of an LS PCI that gives you the ConnectX-5. As you can see, it says there the virtual function. So that means that Infiniband partitions are being enabled. This partitioning is what we use to share, to allow the different customers to share the same Infiniband network and still make sure that the security is provided that they expect. That being said, with partitions, that means you don't have to run your own subnet manager. We are providing the subnet manager. And one step further, you don't have access to VLAN 0. So that means that all your management Infiniband tools will not work. IB traceroute and stuff like that will not work because they require access to the management VLAN 0. So how to actually use that and how to make sure that if you spin up 2 VMs, that you land in the same physical cluster. There are 2 main ways of doing that. The first one is setting up an availability zone, and with an availability zone, you're actually using it a little bit in contradiction with the goal of the design of that feature. If you look for a web server setup, for example, what you want with an availability zone is have 2 copies of those servers serving the web pages. And if one of the zones is being disabled due to a maintenance or whatever, you want to make sure that not the 2 servers are being disabled at the same time. So by creating an availability zone by default, you say that you want to be at least in 2 availability zones. And with that, make sure that if one machine goes down, the other stays up. For Infiniband, we want to use it the other way around. So you want to make sure you're in a single zone. And with that, by setting that, you force the VMs to be landing on the same physical cluster, and that enforces and that allows the Infiniband connectivity. The alternative is to use virtual machine skill sets, and basically that gives you that Infiniband connectivity by default. The other advantage of the virtual machine skill set, if you want to spin up multiple nodes, the amount of API calls are drastically reduced by a lot. And since you only have around 1,200 API calls per hour, the speed up of which you can deploy your VMs is very much improved. We do have some additional abstractions of using availability zones or VMSS. One of the ways is using Azure Cycle Cloud for orchestration. Through that, we have support for different schedulers like SLARM, like PBS, LSF. And through those different schedulers, we can also combine multiple VMSS in a single running HPC cluster. And that allows you to scale the total number of VMs above the total number that can be in a single stamp. Okay, a lot of information. If anyone wants to recheck that, please check out the recording. Otherwise, start asking questions after this session. So now how to use that. We have seen from Thomas already a great explanation of how to install and run EasyBuild, so I won't replicate that one. Basically, we are running here through SLARM with a simple script, just using the OCU benchmarks to verify that we actually have Infiniband connectivity. I load the module. I do an scontrol show hostname to make sure that my jobs that I got are in the host file. And then is one thing we have to do today in the FOSS 2020 or the GOMPI 2020 stack to make sure that we are actually using UCX for the Infiniband is we have to do this export the OpenAPI MCA export. That is not going to be required when we are moving forward to the FOSS 2021A, because there's a new version of OpenAPI and then it is auto-detecting UCX properly. But for now, we need it. When starting then the MPI run, on the left you see the latency with our RDMA on Infiniband, so that is roughly 1.5 microseconds. In the second table, you see if it's using the TCP stack, so going over the Ethernet layer, and you see that the latency there is significantly longer. On the right, also as a verification, we do also a bandwidth test, and that shows you that we can get roughly up to 11 and a bit gigabytes per second. And with a 100 gigabit Infiniband network, that pretty much aligns. Good. Davide, do you take over?
Okay, yep. So I'll take over and I'll show you a little bit some of the results we obtained by running WRF from Easy on our cluster. So first of all, I want to do very important disclaimer. I mean, the target of this exercise was not to try to achieve the best possible performance, but that of making sure that Easy is fully compatible with the with Azure and our infrastructure, so that Infiniband works out of the box and no additional tinkering is needed from a user perspective in order to work. If we can go to the next slide, thank you. So here is a typical, a very simple SLARM script. This one was run on a cluster in the cloud cluster. One of the, as you can see, it's relatively simple. I have the only difference is that you know, as you can see, we source the Easy init script within the job, so that we make sure that on the landing compute node, CVMFS is loaded. Then aside from that is not needed, because MPI will automatically look for the executable as absolute path. So as soon as all the other compute nodes will try to reach the executable, the CVMFS will be automatically mounted at runtime. The only thing we needed to do to run correctly on our HBv3 that has the Milan processors is to override ArtSpec to make sure that it picks up correctly Zen 3. That's something that we will definitely have to work on, so that it's it will be correctly recognized without additional override in the future. Aside from that, simply load the WRF module, set up the input, and then in the end just run the MPI, just run MPI run with WRF executable. In this case, since both SLARM was natively built with PMIX support, there was no need for additional requests for nodes directly in, or for number of cores per node in the MPI run statement, because that's automatically passed through SLARM. So that's very simple, and this one definitely shows the huge benefits of using EZ in terms of user simplicity. Can we go to the next slide? Thank you. So here are just a couple of plots. And again, not looking at I'm only looking at how it works. So here we're not looking at absolute performance. But on the left, you can see the total runtime for WRF. In this case, we have used the CONUS 2.5 kilometer sample, which is the bigger of the two CONUSes, so that we have enough workload to actually scale over many nodes. And as you can see on the left, we have separated the total time from the compute time. That because in order to make sure that our DMA and the scaling was done correctly, we calculated the parallel efficiency and the scalability by using just the compute time, which is the one that is directly related to the RDMA. And as you can see from the right side, the parallel efficiency is, so WRF showed superlinear behavior, which is typical of memory-bound codes, all the way up to 16 cores, to 16 nodes. And in this case, we have used a very simple setup. You are not using any OpenMP or hybrid parallelism. We are just using one thread per core and all 120 cores per node. So we are just doing it the most vanilla way possible. For sure, there is room for optimization and room to make it go faster. But for now, we are very happy to see that just, out of the box with no particular changes, it just performs great. Can we go? Thank you. So just a quick look at what is, at this point, what are the next steps. So one I already mentioned, which is to optimize the WRF runs. And so, for example, what would be the benefit of tiling or using MPI processes or OpenMP, or doing different types of partialization of the workload across the different cores. And also from an IO perspective, how can we optimize the IO timing so that the performance, so that the total runtime also scales as good as the compute time. Another one is also to add WRF 4. That's also something that we are working on. And then from there to try to see how much we can scale. So until now, we stopped at 16, but definitely we want to go much, much larger than that. So we feel very optimistic about that. Another one is to use Reframe to start regression testing automation on our fleet. So to integrate EZ into a more continuous process of checking that our fleet of VMs is actually performing correctly, not just from the point of view of are they healthy, but also do they perform right, which is two, as you know, which are two complete separate things. From a more easy centric perspective, one of the things that we would like to discuss with the EZ community is what would be strategies to better optimize the deployment of EZ from a CVMFS perspective on the cloud. So about for example, regarding the deployment and management of Stratum 1 in different Azure regions. So would it be better to deploy them over VMs as it is currently done, or for example, to provide it directly through Blob? And another thing, another food for thought is, will there be a need for Squids, and especially possibility of auto scaling. So the idea here would be if a specific, if squids are required for a specific deployment, it would be possible to make sure that as soon as a squid receives up to a certain amount of connections, then a new squid is deployed and then scaled back when the squids are sitting idle. In this way, you will have ability to scale up your bandwidth by allowing more and more connection coming up and then scaling down when the connection is not there anymore. And obviously we are, as we said at the beginning, we are eager to collaborate with you guys. So anything that you might feel like that we can do to make to run HPC in a better way, in an easier way with Easy, we are here and happy to get your thoughts and ideas. And
time for questions.
Yep.
Yeah. Okay. Yeah. While others maybe are thinking about a question, I have one or two. Let me do the second one first. Have you evaluated the impact of running WRF, of using WRF installations that were not fully optimized for AMD Milan? So in Easy you have Zen 2, for example, also the fully generic binaries that should run anywhere, or even the Haswell binaries, I think, should also work on Milan. Have you assessed if the performance impact of using the wrong binaries on the Milan nodes?
So I have not done it in an analytical way, so in a sense of exactly answering that specific question, but that was one of the things that we have done before overriding, in a sense that our first attempts were like, okay, let's easy do the job. So ArchSpec at that point was picking up Haswell, I think, and he was like, yeah, okay, I'm just gonna go down and use Haswell against it. And from a performance standpoint, yes, there was an impact compared to Zen 3. But again, after that, we did the override and we targeted directly Zen 3. So I do not have now an answer for what is the performance impact. And again, we were not really focusing on performance here. So that's definitely something that we will be happy to do in the next step. So once we reach a point where we say, okay, now we have a configuration that we know the WRF performs at the best, then at that point, yes, we can try and see what is the difference of, for example, running generic versus.
And then
to add to that, I think sort of like the optimizations within the IO layer are more significant than the optimizations on the compute side. Looking at the initial results.
And that's mostly an issue with how the WRF job was configured, not so much with the software available in Easy, or is there something to gain there as well?
No. It's the CONUS is a significant data set, and that is being distributed initially over all the nodes. So there's a significant amount of bandwidth required to do that. And basically we weren't using any highly optimized shares there to do that. We have the possibility to use either NFS or Lustre, and we didn't have it at this time. It was just plain NFS and nothing spectacular there.
Right. Okay. And a follow-up question, which I think may be relevant in terms of scaling, what you've been mostly focusing on here. Have you looked at the impact of loading software from CVMFS and comparing that with loading from local disk? So especially when you go to larger runs, 16, 32, 64 nodes, are you seeing any impact there from, especially in MPI startup, where all those runs are basically waiting for those WRF binaries and all the libraries to become available before anything can really happen?
To be honest, not at this time to that detail. And I think the current setup of sort of like the 60 nodes are not significant enough to start noticing. We do see the impact if we compare this, and that's what's not done with this particular application. That was done in another project where I've seen significant differences when running from a container registry versus running from NFS. So it is definitely part of the plan to look at those three solutions and compare them. But then I want to be running at least sort of like, I would say 64, 128 node range before that really starts to make an impact.
Mm-hmm. And that's probably also when the squids become relevant, that you have a squid close by that has maybe a hot cache for WRF or the cold cache for WRF, and then all these things are coming into play as well.
Yeah. That is what we expect, and that is why we are also eager to sort of like start. I mean, this was really for us capability. Can we start using it? Can we start doing this? Now we can start making plans on what are the right directions to optimize.
Mm-hmm. Yeah, this is maybe also something interesting to couple back to the CVMFS developers, because we asked Dave yesterday, who was talking about CVMFS, whether they have looked at let's say the impact of CVMFS jitter on large scale runs, and it seems like they haven't really done that, or they're not aware of any studies there. So looking in that direction, it seems like there's an opportunity for collaboration there, maybe even with EasyBuild and CVMFS and you guys to take a close look at that and what the problems are and how they can be mitigated and on what scale it starts becoming relevant.
Yeah, one of the interesting things, and that is, I have to be very careful with these remarks because it's not my specialty. I'm not working with them on a day-by-day basis, but in a lot of the environments where, for example, the Atlas project or something like that, from a distance, it appeared that those are mostly high throughput runs. Mm-hmm. Yep. And that means that the synchronization that is required to do an MPI init is not there. And it's going to be interesting to have these MPI workloads and see how that influences that, where we already seen sort of like the requirements on container registry and sort of like we roughly know where the boundaries are for those.
Yeah. And I can imagine things that you may come to a situation where having a squid proxy per rack or something, so to basically have really local squids could become interesting. Yeah. For really large scale stuff. So I think it's an interesting thing, especially if they haven't looked at this closely, because I know they have some ongoing work on improving the loading time for Python applications, for example, where you're hunting lots of stuff down in the file system. And that's where you can really feel the latency of CVMFS. So they have some prefetching or preloading things going on there that they're actively working on, which could maybe also be relevant in the scope of MPI workloads.
Yeah. Absolutely. And anything Python based is going to need optimizations, because those want a high IO capable NFS share, and that is where they feel the most comfortable.
Mm-hmm.
Yeah, the first test I've done on a very simple CVMFS deployment, I did it with TensorFlow. So just module load TensorFlow and then go into the Python interpreter and do import TensorFlow and then just time that. That's a very useful benchmark.
We see some additional questions in the chat here in Zoom by Bjorn, for example. I'm not sure if Bjorn is still around or wants to raise that himself. If you do, Bjorn, maybe raise your hand and we can let you raise the question yourself. or if not, we're happy to raise it. So his question was what was the domain size for those wharf runs, and are any nestings involved?
Oh, good question. We haven't looked at that at all. This was just plain CONUS. Don't look at the tiles yet. Just run the default 2.5 benchmark. That's it.
Yeah, and I think that Timothy provided the answer on what is the default tiling, and I think that's correct. Yeah. So it's a 1501 times 1201.
And there's also a remark from Kurt, which I think is a good point, where you need, especially on Zen 3, you need very recent compilers, because in GCC 11 they had a Zen 3 option, but it wasn't really doing anything. Well, GCC 10 at least. So in GCC 11, it really starts to do some custom things for Milan. While the 2020A still has, I think, 9.3. So that's maybe too old to really see any big impact from Zen 3 specific installations, but that will change going forward.
Yeah, that being said, a lot of the benefits of Zen 3 are also within the cache layer and pure memory bandwidth. So there's no compilation optimization required at all. You just basically get it for free.
There's actually stuff that GCC does as well, based on how big the caches are. So it will tune the binaries differently based on how big the caches are. So that could actually have an impact already by itself.
Yeah.
But that's probably very workload dependent as well, how much impact that is. Then a follow-up to that, Intel is faster, but may not be possible for the settings. Is that Intel compilers being faster on Zen 3? I'm not sure if that's true. That would surprise me at least. Okay, seems like there is some interesting stuff there.
Yeah, and again, I think that's a room where a deeper collaboration between us and the EasyBuild and Easy community might definitely mutually benefit, in a sense of, okay, now let's optimize, let's work together to get it work, because it's on our interest and in your interest. And
yeah, stuff like providing very recent compilers and Easy, that's not a problem at all. It's not something we focus on. But if that can help with any of the experience you're doing, we can do that overnight, essentially. So that's not really an issue. And maybe coming back to Intel, right now we're of course focusing on open source software in Easy. That may change as well, but there we may have to talk to companies like Intel or NVIDIA if we can actually ship their non-open source stuff through Easy as well. We've tried to talk to them, and maybe they didn't really understand what we were doing, or we didn't explain it well. So we've been trying to do our homework a bit better there, so we can step to them with a more coherent story and explain them what we're doing now and what tricks we have to pull to get things working. And yeah, how much easier that would become if we can just ship CUDA along with Easy itself. So that's an ongoing conversation as well, let's say. Okay. Yeah, thanks a lot for the great talk, and also for the support you guys have been giving to the Easy project. That has been really helpful already, and I'm sure there's lots more to come there going forward.
Yeah, by the way, as a final remark, I've been working, especially in the first hackathon, I've been doing quite a bit of hours on the Easy project. In the second hackathon, I wasn't as active as I planned. That being said, I thoroughly enjoyed being part of the hackathons and looking forward to any future engagements there. Thanks very much for the whole team.
Yeah,
we don't have concrete plans for next hackathons yet, but it's likely we'll have another one before summer, and just see what we can focus on then. Cool.
Sounds good.
Thanks a lot.
Thank you.